Topic is AVL trees, and these are the things I am going to discuss in this one. That is what is binary search tree, drawbacks of binary search tree, how binary search tree can be improved, what is an AVL tree, how the rotations are performed in AVL tree, and how to generate a AVL tree or create a AVL tree from given set of keys. Let us start with binary search tree. This is a binary search tree. Here the keys are arranged such that for any node, all the elements on the left hand side are smaller than that node, the elements on the right hand side are greater than that node. Means for any node, the elements in the left subtree are smaller than that key element, and the elements in the right subtree will be greater than that element. So 30 is greater than 20, 10 is less than 20. So in this way the elements are arranged. Reason, it is useful for searching. How? Suppose I want to search for a key element, say 30. Then I'll start my search from root. I'll check with the root element. Is it 30? No. 30 is smaller than that key element. So go on the left hand side. Now is it 30? No, this is not 30. 30 is greater than this key element. So go on the right hand side. Now right hand side, yes, this is the key element found. So total 3 comparisons we got the element. Let us take one more. If I am searching for the key element 60, then is it 60? No. 60 is greater than this one. So go on the right hand side. Is it 60? No, 60 is greater than 50. So go on the right hand side. Yes, I got the element. So only in 3 comparison I got this element. Let us take one more key. Suppose I want to search for a key element 32. Let us search for it. Start from here. This is not 32. 32 is less than this one. So go on the left hand side. This is not 32. So 32 is greater than this one. So go on the right hand side. This is not 32. 32 is greater than this one. So try to go on the right hand side, but there is nothing. So now search fails. So for this we cannot find the element. So the point here is that when you are searching for a key element, possibility is either it can be found or it will not be found. So search may be successful also, search may be unsuccessful also. But when the search for unsuccessful, how many comparisons I made? 1, 2, 3. So total 3 comparisons. So maximum number of comparisons required for searching any element in a tree depends on the height. So the time taken for searching in a binary search tree depends on the height. Usually we mention height starting from 0 onwards, but I will take from 1 onwards. 1, 2, 3. So let us say height of this binary search tree is 3. So the time taken is dependent on the height of a binary search tree. So this is one of the property of a binary search tree, that is useful for searching purpose. The elements are organized, smaller on left side, greater on right side, and the time taken for searching is depending on the height. Now the question is, what is the height of a binary tree? Like binary search tree is nothing but a binary tree only. What is the height of a binary tree? Height of a binary tree can be minimum log n and maximum n. So it depends. For same set of keys, we can form different binary search trees. It may extend its height up to n also, or it may reduce its height to log n also. So it means the minimum time taken for searching in a binary search tree may be log n, maximum time may be n. So let us observe the next thing. What is the problem with binary search tree? Let us see how to create a binary search tree. I have set of keys here, and the same keys I have taken here also in the different order. Something I want to show you by creating a binary search tree. Let us first create a binary search tree for these keys. What is the method of creating a binary search tree? So we have to insert one element at a time. So first key element, that is 30. So there is nothing. I have taken 30 here. Now inserting 40. 40 is greater than root, that is 30. So insert 40 on the right hand side. Then 10 is smaller than root, that is less than 30. So insert it on left hand side. Then 50. Check from root. For every element we should check from root. 50 is greater than 30 and it is greater than 40. So insert it here. 20. 20 is smaller than 30. Come this side, left side, and 20 is greater than 10. So insert it on the right hand side. The next is 5. 5 is smaller than 30. come to left side, it is less than 10, it's smaller than 10 also, so insert it on the left hand side. 35 is greater than 30, go to right side, less than 40, so insert it on the left hand side. See, suppose if I am inserting again 50, then start from here, 50 is greater than 30, 50 is greater than 40, 50, it's already 50, 50 is already present here, so don't insert it. So we don't insert duplicates in a binary search tree. Now this is the binary search tree I got based on these key elements. What's the height of a binary search tree? This is minimum height, that is log n. What will be the time taken for searching any key element in this one? It will be log n. That depends on the height of a binary search tree. So height is log n. So for the set of keys, when I have created a binary search tree, I got this height. Now same keys, I have taken them here also. See, 50 is there, 40 is there, 35, all the keys are as it is. So but the order is different. Now let me create a binary search tree for that. Start from the first key element, 50. Next is 40. 40 is less than 50, so it will come as a left hand side. Then 35 is less than 50 and also less than 40, so it comes on left hand side. 30 less than this as well as less than this, so it will come on this side. Then 20 is smaller than, it comes this side. And 10 come on this side and 5 comes on this side. So this is the height. Height is what? N. Height of a binary search tree is n. See, the keys are given such that the binary search tree when I am creating, it is becoming height n. So this is the problem with binary search tree. The method of creation is we insert one element at a time. The method I have shown you. But what will be the final height? That is not under our control. The height may be log n also. The height may be order of n also. It depends how the key elements are inserted. If the height is log n, then the time taken for searching is log n. And if the height is n, then the time taken for searching is n. And it is similar to linear search then. If I have to search in this binary search tree, it is similar to linear search. Like see, if I want to search for 5, then I should start from here. 5 is smaller than this and smaller than this and smaller. So finally, how many comparisons? I have to make all 7 comparisons. So this is the problem with binary search tree, that height is not under control. It all depends on how keys are inserted. So this is the drawback of binary search tree. Next, can we improve binary search tree? Is there any chance? Let us look at this. I have 3 keys here. Let us create a binary search tree using those keys. See, these keys, if I insert them and create a binary search tree, then the tree that I will get is 30, then 20 is smaller than that, 20 comes on this side, and 10 is smaller than that, it comes on this side. So what is the order in which I have inserted? I have first inserted 30, then 20, and then 10. Can I insert the same keys in a different order? Yes. There are many orders possible for the same set of keys. So if I am getting the keys like this, then this is the tree what I am getting. If the order is different, let us say it is 30, then 10 and 20. Then how a tree looks like? So 30, 10 is smaller than this, so it comes this side. 20 is smaller than 30 but greater than 10, so it comes on this side. So this is the shape of a tree I am getting. And can I take a different order? Yes, I'll try a different order, that is 10, 30 and 20. So this is 10 and 30 is greater, so it's come this side, and 20 is greater than 10 but less than 30, so it comes this side. This is another shape I am getting. If I take 10, 20 and 30, then this is 10, 20 is greater and 30 is greater than that. So for different orders, I am getting different shapes. So for 3 keys, how many orders are possible? 3 factorial orders are possible. That is 6 orders are possible. So 4 already I have taken. So I will take 2 more. 2 more are possible. That is 6 are possible. So 2 more I will take. That is 20, 10 and 30, or 20, 30 and then 10. Let us create 20. It comes here. 10 is smaller than this, so 10 comes this side. 30 is greater than this, so it comes this side. And for the next order also, 21st, then 30 comes on the right side, 10 comes on the left hand side. So I am getting a tree like this. So it means that for the same set of keys, if I insert them in different order, I am getting different shape of binary search trees. If you look at these trees, the height of these trees is 1, 2, 3. All these trees are having height 3. For just 3 keys, height is 3. So these are with maximum height. But this tree is of height 2. So this is of minimum height. So this means that if you have some set of keys, you can form a very long binary search tree also, or a short height binary search tree also. So what we prefer is a minimum height binary search tree, so that the search time can be reduced. This is the objective. So the drawback of binary search tree is that for same keys we can get different shape binary trees that can be of maximum height or even of minimum height. What we prefer is we want minimum height binary search tree. So now let us see whether binary search tree can be improved or not. See, for the same set of keys, if I am getting in these orders, I am getting this shaped binary search trees, but I want this one. Is there any way to convert this? So there is no way, just we say that just remove it and take this one. If you are getting any other shape, just take this one. But there should be some method which we should define, some procedure for converting that one into this one. So for that we define rotations. We say that we rotate this tree around this node, that is, we'll pull this 30 on this side. So 20 will move up and 10 will move at this place. So we say we will perform rotation around this node and we will change the shape of this node like this. And similarly we'll rotate this tree around this node and we will change the shape. So 10 will come down, 20 will come this side and 30 will come this side. It's just like you imagine that is a nail fixed here and around that is a thread and you are pulling a thread. So if you pull that thread here, 10 will come this side, 20 will move up and 30 will move up. So we say that we will perform rotations and convert this larger height binary search trees into smaller height binary search tree. So this is how we can improve, and this gives the idea of AVL tree. Then how about this? How do you perform rotation? So in one step we cannot do. First we'll rotate around this 10. So 10 will come this side and 20 will come up. Then we'll rotate around this 30. So 30 this side and 20 will move up and 10 will remain on the left hand side. So we get this shape. And here also around 30 will rotate in this direction. Then around this 10 will rotate in this direction. So we will have 4 different type of rotations which we can convert binary search tree into a balanced binary search tree. So that is the idea of AVL tree. So in any shape we want this shape. Now you may ask one thing, that just we have 3 nodes here. What if we have many nodes in a binary search tree? How rotations are done? So remember, rotations are done only on 3 nodes always. Whatever the size of a binary search tree may be, we look for only 3 nodes and we try to arrange them or adjust them by performing rotation to get a tree like this, and the entire tree will get balanced. Entire tree will be of minimum height only. So this is based on 3 nodes only. Now I am going to explain what is AVL tree, then I will show the rotation, then I will show how to create a AVL tree. Now AVL tree. AVL tree is a height balanced binary search tree. So for balancing the height of a binary search tree, we define one factor or one property, that is balance factor. We calculate balance factor for each node. What is balance factor? Height of left subtree minus height of right subtree, and in short it can be written as balance factor is height of left subtree minus height of right subtree, and it should be either -1 or 0 or 1. Not greater than 1, not less than -1. If any node is having balance factor out of these 3 only, then the node is balanced. Otherwise the node is imbalanced. If any node is imbalanced, we should do something for balancing it. That is, we should perform rotations for balancing that one. How to calculate the balance factors? Let us see. One more formula I have written here, that is absolute of balance factor should be less than or equal to 1. Means minus or plus, if you take it as positive only, then it should be either 0 or 1, positive 1. So we'll use this one. Now here I have some binary trees. There are no keys, just I have taken empty nodes, unlabeled nodes. Now let us see what are the balance factor of this one. So how to calculate height of left subtree minus height of right subtree. For this node, what is the height of left subtree? So you take the longest distance in the left side, 1, 2. And the longest distance on the right side, 1, 2. So this is 2 minus 2, this is 0. Same way, for this node, the longest distance on the left side is 1. And right side there is nothing, so 0. 1 minus 0 is 1. And for this one, left side it is 1, right side it is 0, so this is also 1. And there is nothing on left and right, so it will be 0 only. So for all the nodes, we got the balance factors as 0, 1, 1, 0, 0. These are within this set only, so this tree is balanced because every node is balanced. Now let us look at this. For this node, 1, 2, 3. Height is, I am counting edges, okay? The longest path you should take. Don't count the nodes. We are not counting the nodes. We are finding the height. So 1, 2, 3. Minus 1. So this is 2. This is imbalance. The node is imbalance. Let us look at others also. This is 0, left side. Right side is 1, 2, 2. So this is minus 2. So this is also imbalance. This will be 1 minus 0, it is 1, this is 0 only and this is 0 only. Let us calculate for this also. Left side is 1, right side is 1, 2, 3. So I am taking height, right? So this is 3 and this is minus 2, it is imbalance. See, I am not counting nodes 1, 2, 3, 4, not 4, height. So take the longest distance. Now for this the balance factor will be 0. Leaf nodes will have balance factor as 0. This is 0 minus 1 minus 1. This is 1 minus 2. 1 minus 2 is minus 1. That's all. These two trees are imbalanced. They are having some nodes which are not height balanced, but this tree is perfectly balanced. Now we'll learn about rotation. If any node is imbalanced based on the balance factor, then rotations are performed for balancing that node. So let us learn what are the rotations. Now we'll go for the first rotation. The name of the rotation I'll write afterwards. Let us look at this. I have a binary search tree, the initial binary search tree, just there are two nodes, 30 and 20. Let us check whether it is balanced or not. The balance factor is 1 and 0, so this is 1 and this is 0. So this is balanced. Now in this tree, if I insert 10, then where 10 should be inserted? 10 is smaller than 30, it goes on left side, and it's less than 20, it goes on left side, and there is no 10 here, so I can insert it 30, 20 and 10. It is inserted on this side. Now count the balance factor. This is 0 and this is 1 and this is 1, 2 and that side 0 only. So this is 2. So this node became imbalance. That node became imbalance. Now I have to perform rotation for balance that one. But let us see why it became imbalanced. This became imbalanced because I have inserted on the left of left. So this is left of left imbalance. Let us call it as left of left imbalance. Now I will perform rotation. After rotation, what type of rotation I should perform? See, for this node, the balance factor is 2. So it is heavy on the left hand side. If its balance factor is minus 2, then it means it's heavy on the right hand side. Okay, I don't have to check which side it is heavy. But one important thing is this node became imbalanced because we have inserted on left of left. So perform this rotation on this one over this node. So over this node will perform this type of rotation. So how it looks like, 20 will move up, 20 moves up, and 30 will move to the right side and 10 will take the place of 20. 10. Now this is perfectly balanced. This is balanced. So because this was LL imbalance, I have performed this rotation. So let us call this rotation also as LL rotation. That is left rotation. So this is the first rotation. This is initial tree, 30 and 10. Balance factors are, this is 0 and this is 1. Now I will insert 20 in this one. So 20 is less than 30, it goes on left side, but greater than 10, so comes on right side. So 30 here, 10 on the left hand side and 20 on the right hand side of 10. Now let us calculate balance factors. This is 0 and this is -1 and this is 2. Again this node is imbalanced. Why it became imbalanced? Because I have inserted on the left and then right. So this is LR imbalance. LR imbalance. Then you remember I said that whatever the binary search tree you get with 3 nodes, we will take a balanced tree. We want that one. So on this we have to perform rotation. So the rotations, these are 2-step rotations. So I will write down here 30, 10 and 20. So first we'll perform rotation on this one. So how it looks like, 30, then 20 comes here and 10 comes here. So we have performed rotation over 10. Pull 10 this side by fixing a nail here. So who will move up? 20 will move up. That will not be affected. So 10 is pulled this side. So 10, 20 will move up. It looks like this. Now perform this rotation. If you perform this rotation, again the result is 20 will be in the root and 10 will be on the left hand side, 30 on the right hand side. This way. Now this is the fixed point over which the rotation is done. So 30 is moved that side, 20 moves up and 10 moves up. That's it. So this is 2-step rotation. This is not 2 rotations. This is double rotation. We count this also as one rotation only, but this is having 2 steps inside. So we call it as a double rotation. Now what is the name of this rotation? The imbalance was left-right type. So let us call this rotation also LR rotation. So far we have seen 2 rotations. That was LL rotation. It was single step. Then LR rotation. It is double steps. 2 steps are there. Now similarly we have 2 more rotations. I will quickly cover them. This is initial tree. The balance factors are 0 and 1. Now insert 30 in this one. 30 is greater than 10 and greater than 20. So 30 comes on the right side of 20. Then the balance factors are 0 and this is -1 and this is -2. So this became imbalanced. So which type of imbalance? Because we have inserted on the right of right. So this is RR imbalance. When RR imbalance is there, we'll perform this type of rotation by fixing this node. We'll pull 20 here. So 10 here, 20 will move up and 30 will move up. Right? So it looks like this again. And the balance factors will be 0, 0, 0. What was the type of imbalance? RR. Let us call this rotation also as RR rotation. So this is the third rotation. Again, this is a single rotation. Now next rotation. Initially the tree is 10 and 30. Balance factors are 0 and -1. Insert 20 in this one. 20 will come as right side of 10 but left side of 30. Balance factors are 0 and 1 and this is -2. So this node became imbalanced. So how it became imbalanced? The insertion is done on right left. So let us call this as RL imbalance. Now for this also 2 steps are required, that is double rotation is required. So that tree 10 and 30, 20, first it is rotated around this one, then 10 comes here and 20 and 30 comes here. Then perform rotation over this one, over this node, then the tree looks like this. The imbalance is RL, so the rotation is also RL rotation. So that's all. These are 4 rotations. And now I will show you how to create a AVL tree by inserting keys one by one. So we have seen total 4 rotations, out of which L, L and R are similar. These are single rotations, and LR and RL are similar. These are double rotations. Now I am going to show you special cases in these rotations. Suppose a binary search tree is like this. These are the nodes A, B, C, and A is having some right child, that is right child of A, and there is B is also having some right child, and C is having left child and right child. So it means it's a very big tree. Don't know how many nodes are there below this one. So we have just taken it as right subtree of A. So any number of nodes below that one. But suppose this node became imbalance. This node became imbalance because of insertion on the left of left, this side. So LL rotation, how to perform this one? We have to perform rotation around this node. LL rotation means assume that insertion is done on left of this A, and A became imbalanced. So let us look at how rotation is done over that node, LL rotation. So don't look anything, just look at ABC and draw this one. So this is B and C and A. As I said, rotations are done always within 3 nodes. Now what about others? C left child, right child, they will be as it is. C left child and C's right child will be as it is. Then A right child will also be in its own place. Then what is missing there? B's right child. So this is right subtree of B, so it should be on the right hand side of B only. Then where it should come? Where is the space remaining? Here is the space remaining. So B's right child will come here. B's right child will come here. Alright. So this is, you can take it like a formula or an example in a big size tree with lot of nodes beneath this one. Just we are looking at these 3 nodes, out of which this node has become imbalance. So this is how we perform rotation. I have shown you LL rotation. It will be similar for RR rotation also. It will be from that side. This means that, see, if I remove everything and just take this one, see, imagine there is some nail fixed here and this is a thread, and to a thread something is attached. So this is a nail and there is something attached to a thread, and when you pull a thread on this side around that nail, it looks like this. Then what about this thing that is attached? It will go that side and look like this one. So same thing has happened. A, B, C, and B was having right child. When you pull this on this side, A on this side, so A goes there, and what happens to BR? It will come as a left of A. Removing all this, if you just see this, the effect is similar. Or if you keep AR, so AR is as it is. It is just like there is a thread and a nail, and you are pulling a thread on that side, something is attached to a thread. So after pulling that side, this thing, right, if it goes there, the stick like thing which goes there, so it looks like this. This is the shape. So the same shape we are getting here. So that's all about LL I have shown you. Same thing you can apply on RR. Now let us look at LR rotation. This is a binary search tree. I have not taken a big size tree. Let us first look at just 3 nodes. Suppose this node became imbalanced because of insertion on left right. So we'll perform LR rotation because it is LR imbalance. So already I have shown you how this rotation is performed. First step like this, then second step like this. But finally, what will be the result if first step is performed? A, B on this side, and C on this side, and B comes here. Then again, when this rotation is performed, C goes here and B remains here and A will be on the right side. It looks like this by taking 2 steps. I'll remove this. By taking 2 steps, it looks like this. Now, can we show it in a single step? How we can show it in a single step? Just see this. We can say that When you have to perform LR rotation out of 3 nodes, the last node, just you bring it into root C, left side is B only, then A, you take it on right side. That's all. We say that we can directly, always rotation is within 3 nodes only. Out of these 3 nodes, last node you bring into root, and the root you send it on the right side because it is LR rotation. In RL rotation, you can bring root on the left side. So LR and RL will be same. So I have shown you how we can directly perform LR rotation without looking at these 2 steps. Directly we can bring this node up here and send A on that side. Now let us look at how it is done on a bigger size tree. If I have a tree like this, A, B and C on this side. So A is already having its right child, B is having its left child, and C is having left child, and C is having right child also. And this became imbalance, and imbalance is LR imbalance, LR imbalance, and I have to perform LR rotation. Now they are already having some children with them, their subtrees are there, then how rotation is done? Out of 3 nodes, as we know that this should move up. So C will move up, B remains as it is, A will come on the right side. Now what about the left child of B? It will be as it is. What about the right child of A? It will be as it is. Now who are remaining? Left subtree of C, right subtree of C. Left of C will go in the left side only. So C is here now. So its left child will be on the left side only, but it will become a right child of B. And right subtree will remain on the right side only, but it will become a left child of A. This is the method. You can take it like a formula now. I have shown you that when you have to perform LR rotation, we can perform in a single step directly. So that single step I have sent it up. So B on this side only, A have moved to the right side, then rest of the children are arranged. So this is like a formula like you can take it and always follow this method. Now the last thing is I will take some keys and show you how our AVL tree is generated. Let us create an AVL tree of these nodes. I will insert them one by one. We will calculate balance factors. If any node is becoming imbalanced, we will look at it, which type of insertion is done, why it became imbalanced, then perform corresponding rotations. So let us take this. First key, 40 is inserted. There is a single node and it is balanced. Then insert 20, 20 will come on the left hand side. And balance factors are, this is 0 and this is 1. Everything is balanced. Next is 10. Insert 10 on this side. Now calculate balance factor. This is 0 and this became 1 and this became 2. So height of left subtree is 1, 2. So 2. Right subtree is nothing is there. So 2 minus 0. This is how it is becoming 2. So that became imbalance. Where the insertion is done on the left of left. So LL rotation will perform. LL rotation around this node. So 20 here, 10 this side, 40 here. And the balance factors are all zeros. Now it is balanced. I'll remove this and use that one. Now insert next 25. 25 is greater than 20 but less than 40. So it will come this side. Let us update balance factor. 0, this is 1 and this is 1 and 2. So 1 minus 2, it is minus 1. Perfect. Next, 30. 30 comes on right side of 20, left side of 40, but right side of 25. So 30 comes here. Update balance factors. Balance factors are 0 and this is minus 1 and this is 2 and this is minus 2. This is 1 minus 1, 2, 3. So this is minus 2. Oh, 2 nodes became imbalanced. This is also imbalanced. This is also imbalanced. Now we are learning one more thing. If multiple nodes are becoming imbalanced, which one we should perform rotation? Where you have inserted here. From there you go towards the ancestor. The first ancestor which became imbalanced, perform rotation over that. So this is the first ancestor. So perform rotation over that one. Automatically that will also become balanced. So according to this imbalance node, insertion is done which side? Left, right. So this is LR rotation. So we'll perform LR rotation. LR rotation means what? Instead of showing two steps, we can simply take this 30 up and 40 this side. So this becomes 20 on this side, 10 here, and here comes 30, 25 remains here, and 40 this one. This is how LR rotation is done. Now update balance factors. 0, 0, and this is 1, 1. This is also 0. This is 0. This is 1 and 2. So this is minus 1. Everything is balanced. I'll remove that one. Now next node, 22. Where 22 will come? Right side of 20, left side of 30, and left of 25. So it will come here, 22. Let us update balance factors. This remains 0 only. This is 0, this is 1, and this is 1, 2, and this is 1. So this is 2 minus 1, this is 1 only. What about this? This is 1 and minus 1, 2, 3. Longest distance is 3 here. So 3 is minus 2. So this became imbalance. All are balanced only. You see 0, 0, 0, 1, 1. And that became minus 2. So this node became imbalance. Now one thing to observe. According to this, where insertion is done? Right, left, left. R, L, L. No, just take 2 steps. R, L. Means consider only these 3 nodes. No, we inserted this one now. Whatever it may be, wherever you insert. Who became imbalance? This became imbalance. Then only take 2 steps or 3 nodes from that imbalance node. So just 3 nodes you see. Right? See, even if I have not inserted 22, if I would have inserted 26, it would have came here. Then also insertion is on right, left we say. It will be right, left, right. So will not take all steps. Just 2 steps from an imbalance node. Whoever became imbalanced, from there just 2 steps. So if you just take 2 steps, perform LR rotation. So as per LR rotation, this 25 can be sent up, 25 is sent up, and on this side comes 20. So what about 10? 10 will be remain as a left child of 20, and this side 30 will be as it is, and this is 40. What about this 22 who was left child of 25? It is still be in a left subtree of 25, so it will come this side. 22 will come this side. That's how the rotation is performed like this. We have performed RL rotation. Already I have shown you how RL is performed. Now last key is remaining, that is 50. Let us insert this. 50 comes this side, that is right side of 40. Now if you check balance factor, these are all 0, 0, 0, and this is 1, 2, and 1, 2, 3. So this will be minus 1, and this will be 1, 2. So this is minus 2. And this is minus 1 and 0. So this node became imbalanced. Perform rotation along this one. So which type of imbalance? R imbalance. So perform rotation. So 25 and 20, 10 and 22, they all remain as it is. And this will be 40 and 30, 50. Now it's perfectly balanced binary search tree we got. That is AVL tree. Height balance AVL tree or binary search tree we got. So this is the method of creating an AVL tree. Now one thing to remember, that don't allow any node to exceed the balance factor from minus 2 or 2. You should never get minus 3 or 3. If it is becoming imbalanced, then and there perform rotation. Don't wait that first I will insert all the nodes, then afterwards I will perform all rotations. No, this is not possible. Whenever any node is becoming imbalanced, just after insertion, if any node is becoming imbalanced, then just perform rotation and balance the tree. Now I'll show you one more last situation, then how rotation is done. Let us look at one last thing. A big tree I have taken here. Let us see whether it is balanced or not. Balance factor for leaves will be zeros only. These are all zeros. Then this node 1, 1, so this is 0. This is 1, 2, 1, 2, 3. So this is minus 1. Balance only. What about this one? 1, 2, 1, 2. So this is 0 and this is also 0. This is minus 1. So all nodes are perfect. So they are all balanced. So the tree is balanced. Now I will insert a new node, that is 42. So 42 is greater than 40, less than 50, less than 45, but greater than 41. So 42 comes here. Let us see what happens. I'll update the balance factor. This becomes 0. This becomes minus 1. This becomes 1, 2, and this is 1. So this becomes 1. And this is 1, 1, 2, 3, and this is 2. So this also becomes 1. And what about this? This is 1, 2. So this is 2 minus 1, 2, 3, 4. 4. And this is minus 2. This node became imbalance. Now which rotation I should perform? Where I have inserted right, left, left, right, right, left, left, right. Don't take all steps. Just take first two steps, left, right. Remove this one. I have to perform rotation by using just 3 nodes. So what happens? 45 goes up, 40 moves here. What about all other nodes? Already have shown you the formula how they are adjusted. So just you can follow that and complete this rotation. So that's all. The height of a AVL tree is always balanced. So it's a balanced, height balanced binary search tree. It's a binary search tree only, but it will maintain the height. And it will try to maintain always log n height. It will not exceed to n like binary search tree. So at most the height of a AVL tree is measured as 1.44 into log n. So at most it may be 1.44 into log n. Right? It cannot be always exactly log n. It may be little bigger also, but it will be multiples of log n only. So asymptotically we say the time taken for searching in a AVL tree is log n. That's all about AVL tree. Just like AVL tree, there is one more height balanced binary search tree, that is red-black tree. The idea of red-black tree is also same as AVL tree, but AVL tree is more strict and there may be many rotations performed in AVL tree. While creating a AVL tree, we may be performing a lot of rotations. To avoid that rotations, more frequent rotations, red-black tree is used. Red-black tree is not having that much strict rules as compared to AVL tree. But red-black tree is also as efficient as AVL tree. So these are two height balanced binary search trees. So we have discussed about AVL tree. That's all about this.